This is Jonathan O'Neildon with the University of Vermont, and this is part one of a two-part series on remote sensing. Let's start with a definition from Dr. Nicholas Short. Remote sensing is a technology for sampling electromagnetic radiation to acquire and interpret non-immediate geospatial data from which to extract information about features, objects, and classes on the Earth's land, surface, oceans, and atmosphere. Remotely sensed data comes from a variety of sources. Aerial cameras, multispectral satellites are perhaps the two most common. Radar satellites and some cutting-edge experimental sensors such as hyperspectral systems are a bit less common. Variety of uses for remotely sensed data. It's more than just a pretty backdrop in our GIS. Transportation, agriculture. Notice on the right here, you can clearly see the effects of clubroot disease detected in color infrared aerial imagery. Natural resource applications. Here we're examining time series data of the Amazon basin. This is the characteristic fishbone pattern of deforestation, where a central road comes in, and then subsequently smaller roads are built off those, and smaller roads in turn are built off of those, creating a fishbone-like pattern. Here we're going to examine some time series imagery of southern Iraq. This is the region that the Marsh Arabs live in. Saddam Hussein was not a fan of the Marsh Arabs as they opposed his regime. Here we are looking at 2000. You're going to notice that the area is mostly dry aside from some agricultural development. But if we go back in time here, we see that the marshes actually used to be quite lush. But here in 1990, you're beginning to see the effects of those marshes being drained. If we go back to 1975, we see that there was substantial marsh habitat there. An example closer to home here in Chittenden County, centered on the Billington International Airport. Over on the right, you're going to notice that the circumferential highway is visible in 2001 and not in 1990. In a GIS, we can combine these images. In this case, red features represent features where brightness values have increased in 2001. Going to notice that we have the circumferential highway clearly delineated along with new developments, but we're also showing that some agricultural fields where there have been changes in management practice are also detected. So this is not a foolproof method for detecting development. Of course, remote sensing got its start for national security purposes. This is an interesting example of the southern Iraqi oil fields prior to the start of the Iraq War in 2003. Over on the left here, we're looking at a true color representation of some oil wells. The smoke that you see there is a practice of burning off natural gas from the well. Over on the right, we're using thermal or emitted energy to detect the actual hot spots of those oil wells. In this case, it allows us to precisely count the number of oil wells. One of the interesting things about the prevalence of commercial satellite imagery is it allows other organizations outside of national governments to do everything from humanitarian monitoring, such as you see in the center picture there, of villages in the Darfur region, to even assessing weapons of mass destruction, such as that picture on the right there of a nuclear reactor. Example here of some change detection, showing areas when they were cut in the forest. And here we are using the IfSAR satellite to map the urban heat island effect in the greater Boston area. Blue is cold, red is hot, and if we overlay a road network, you can see here very clearly shows the areas of high population density corresponding to higher roads and increased heat. To understand remote sensing, we have to understand electromagnetic radiation. Energy from the sun travels to the Earth through space as electric and magnetic waves, or electromagnetic radiation. The range of electromagnetic radiation of various wavelengths and frequencies, extending from cosmic waves to radio waves, is known as the electromagnetic spectrum. As humans, we sense a relatively small portion of the electromagnetic spectrum. That is, we sense visible light. Visible light contains three primary colors, blue, green, and red. And our eyes, much like the majority of the sensors out there, are passive detectors. So we have a source, the sun in this case, that essentially emits electromagnetic energy. Some of that is scattered, it's irradiated down, comes through the atmosphere, where it reaches features on the Earth's surface, such as those trees. It's reflected where it's detected by a sensor. Some of that, of course, is transmitted, it's absorbed, and then it may be emitted later on as heat. So the spectral imagery regions. Over on the left we have the ultraviolet. Those are not commonly used in many of the sensors. The visible portion of the electromagnetic spectrum, that's the most common for sensors, and of course the portion of the electromagnetic spectrum that we as humans sense with our eyes. Then as we move out beyond the visible, we go into the near infrared, also quite common for many of these sensors, particularly in the last couple years. As we move out further from the near infrared, these of course wavelengths that we cannot detect with our eyes, the short wave infrared, the mid-wave infrared, and then finally out to the long wave and thermal portions of the electromagnetic spectrum. It's important to note that as we move out from the visible portion of the electromagnetic spectrum to the infrared, the near-infrared, short-wave, and mid-infrared, those are still reflected portions of the electromagnetic spectrum. It's only when we get out to the end of the mid-wave and into the long-wave infrared that that's the thermal imagery that's actually emitted. So why does an object appear the color that it appears? Well, in this case we have a red flag. So the primary colors, red, green, and blue, come down. They comprise white light emitted by the sun. It strikes the flag. The flag absorbs the blue and the green light, causing it to reflect red light. If we were to plot that out on a spectral response curve, such as you see on the bottom here, we would have a noticeable peak in the red portion of the electromagnetic spectrum. That's because the amount of red light reflected is much higher than the amounts of blue or green light. Different features have rather distinct spectral response curves. Here we are looking at the spectral response curves in the visible and near-infrared portions of the electromagnetic spectrum. Many of the sensors nowadays, both the high-resolution aerial systems and the high-resolution commercial satellite systems, function in both the visible and near-infrared portions of the electromagnetic spectrum. Let's take a look here at that bright green line there. That's the spectral response curve of grass. If we follow that spectral response curve, we're going to see that it has a peak in the green portion of the electromagnetic spectrum. Not surprising, if we look at grass with our eyes, we know it appears green. What's interesting is that as we move out to the near-infrared portion of the electromagnetic spectrum, the spectral reflectance of grass increases dramatically. Now we can't see near-infrared light or NIR light, but if we could, vegetation would appear very bright. Take a look at the blue curve there corresponding to artificial turf. You're going to notice that artificial turf also appears green. So if we were flying overhead, artificial turf and grass would perhaps be difficult to tell the difference from 20,000 feet, but if we could see near-infrared light, those two features would appear markedly different because grass reflects a lot of near-infrared light due to its molecular composition as opposed to artificial turf, which does not. So going out beyond the standard visible portions of the electromagnetic spectrum is one of the true powers of remote sensing. Let's look at an example here of just some oblique photographs. Over on the left here we just have a panchromatic or black and white photograph. Over on the right we're looking at the same photograph, same area, near infrared. You're going to notice that features appear quite different. Specifically those dark trees in the middle there are conifers. And it's the structure of the needles of those trees that causes them to appear differently in near-infrared portion of the electromagnetic spectrum as opposed to the visible portion, which is what we see on the left. Another comparison, over in this case down in the Mad River Valley in Vermont. Over on the left we're just looking at the amount of green reflected energy. As you're going to notice, man-made features reflect a lot of visible light, so over on the left they appear quite bright. As we move over onto the right and look at near-infrared reflectance, we're going to notice that we start to see a lot more differences in the forested areas. We have darker areas corresponding to the coniferous trees, brighter areas correspond to the deciduous trees. You're going to notice we have more variation in the agricultural areas depending on the health of that vegetation. Water features show up quite clearly. Water absorbs practically all near-infrared energy, causing it to appear very dark. You're also going to notice that man-made features don't appear nearly as bright as they do in the visible portion of the electromagnetic spectrum. In a GIS environment, all of the remotely sensed data that we work with is digital, so that means it's composed of pixels. At the very basic level, each pixel has a digital value, or a DN, assigned to it. As brightness increases, that pixel has a higher value. So the way sensors work is that each cell is recorded as a digital number, or brightness value. This brightness value is the measure of the amount of electromagnetic radiation received by the sensor, and the brighter the signal, the higher the value. As we've shown in previous slides, sensors don't just see in one portion of the electromagnetic spectrum. Many sensors have multiple what's known as bands. That is, each band is sensitive to a specific set of wavelengths along the electromagnetic spectrum. And these bands are placed there for a purpose, and the purpose is to maximize the detection of features. Here we are looking at the band display of a satellite known as Landsat. Landsat's been in operation since 1972, and the Landsat has 7 bands. Here we're going to look at the non-thermal bands. So band 6 is the thermal band. We're not going to examine that here. So you're going to notice bands 1, 2, and 3 correspond to blue, green, and red light, all visible light. They're highly correlated, and so those images, things look quite similar. Specifically, man-made features appear very bright. As we move out beyond the visible portion of the electromagnetic spectrum into the near-infrared, band 4 in the lower left there, things change quite dramatically. Vegetation appears much brighter, water appears very dark. As we move further out along the electromagnetic spectrum into band 5, which is shortwave infrared, things change once again. Water is still dark, but also certain man-made features appear bright once again. And then out to band 7, which is the midwave infrared, you can see now that the visible portion of the electromagnetic spectrum, bands 1, 2, and 3, the man-made features are quite similar to that of band 7, but the water features are very dark. So each one of these bands has certain advantages and disadvantages when attempting to map features. However, it's a combination of all of them that can help us accurately identify classes that we're interested in. Remote sensing requires a thorough understanding of color theory. The color theory is additive color theory, so this is similar to when you combine paints on a piece of paper. This is shining light. So there are 3 primary colors, red, green, and blue. The combination of red and green equals yellow, the combination of red and blue equals magenta, and the combination of green and blue equals cyan. Equal amounts of red, green, and blue create white, or the absence of red, green, and blue creates the color black. So red, green, and blue are called the primary colors, magenta, yellow, and cyan are called the complementary colors. Color theory is important because your computer monitor has 3 color guns. So that means when we have a satellite such as Landsat, which has 6 bands, we can display only 3 of those bands at a given time to our computer color guns to create a color composite within our GIS software. Let's take a look at how this works. Here we're going to take individual Landsat bands and apply them to color guns. We're going to take band 3, which is sensitive to red light, and apply it to the red color gun. We're going to take band 2, which is sensitive to green light, and apply it to the green color gun. And then finally we're going to take band 1, which is sensitive to blue light, and assign it to the blue color gun. What this means is features that are red will appear red, features that are green will appear green, features that are blue will appear blue. The resulting image is what's known as a true color composite in this case. Now let's switch things up a little bit. This time we're going to take band 4, which is sensitive to near-infrared light, and assign it to the red color gun. So features that reflect a lot of near-infrared light are going to appear red. We're going to take band 3, which is sensitive to red light, and assign it to the green color gun, meaning that features that reflect a lot of red light are going to appear green. Finally, we're going to take band 2, which is sensitive to green light, and assign it to the blue color gun. Features that reflect a lot of green light are going to appear blue. This might sound a bit confusing, but the resulting image, which is known as a color infrared composite, is very useful from an image interpretation standpoint. You can see in this image depicting the greater New York area that features such as Central Park, along with the expanses of vegetation and the outlying suburbs, clearly appear that reddish magenta color because vegetation reflects a lot of near-infrared light. Man-made features, as we saw in our spectral response curve in the previous slide, reflects a lot of visible light. The visible wavelengths in bands 2 and 3 are assigned to the green and blue color guns. Applying our color theory, we know that green and blue, a combination of those two, yields cyan, and so we see man-made features in this case appear that light blue or cyan color. Another example of image display. In this case, we're looking at a color infrared aerial photograph. With aerial photos, the band numbers are typically reversed, and so this can be confusing, and it's always important to check your metadata. So in this case, we're looking at a color infrared aerial photograph where band 1 corresponds to near infrared light, that's assigned to the red color gun. Band 2, red light, that's assigned to the green color gun. Band 3, sensitive to green light, is assigned to the blue color gun. The result, once again, a color infrared composite. Man-made features appear cyan, vegetation appears magenta, and water features generally appear darker. Some Landsat band combinations here. When you see numbers on the left, such as 321, that's corresponding the bands to the red, green, and blue color guns. So here it means band 3, red color gun, band 2, green color gun, band 1, blue color gun. So this is what's known as the natural color composite on the left. In the center, we have band 4 assigned to the red color gun. That's near infrared light once again. So this is a color infrared composite. And over on the right, we have a pseudo-color composite. Some features appear quite distinct in these images. You can notice, for example, the pond in the upper right-hand corner shows up very, very well in the color infrared and the pseudo-color images in the center and the right. Water penetration is much improved in the true color composite. And when it comes to differentiating types of vegetation, you're going to notice that over on the right there with the 452 band combination, we seem to be able to detect different levels of intensity both in agricultural practices and also within the downtown urban areas. Let's examine some sensor properties. We're going to talk about the spatial resolution, or the pixel size, the spectral resolution, and the number of bands, the radiometric resolution, and the temporal resolution. So spatial resolution, this typically refers to the pixel size. We have sensors such as Landsat, which can be considered to be moderate resolution sensors with 30-meter pixels. Satellites such as Iconos that have a 4-meter multispectral system or high resolution. And then we have even higher resolution, such as our aerial systems that generate orthophotos. The number of bands is important. We may have a single band system that yields a panchromatic or black and white image. We may have multi-band systems, such as the top here, which is an example of the placement of the Landsat bands, in which we have multiple bands, and those are multispectral systems. And then finally, we can have hyperspectral systems with hundreds or even thousands of bands. Radiometric resolution is the ability of a sensor to perceive differences in brightness value levels. So the higher the radiometric resolution, the less likely that we'll have difficulty telling features apart that have similar spectral responses. The top example here shows what happens when you have 256 possible intensity levels. This is called 8-bit imagery because it's 2 to the power 8. Over on the bottom there we have 2-bit imagery, in which case the pixels only have values from 0 to 4 as opposed to 8-bit where we've got up to 256. So the more bits, the higher the radiometric resolution. Typically the easier it is to distinguish features. Temporal resolution refers to how often a sensor can image a given point on the Earth's surface. And there are always trade-offs. There's no perfect sensor out there. So example, in this case we're looking at an aerial photo, a black and white single band 8-bit. That's an on-demand system, very high resolution at 0.5 meter. If we go to Iconos, a satellite system, we're going to see that in this case the multispectral capabilities are 4 meters, not as good as the aerial photo, but with multispectral it's quite easier to tell some of those features. Its radiometric resolution is also higher, meaning that features that reflect similar digital values will be easier to tell apart, and it has a decent revisit time. Then if we go to Landsat, of course its resolution is much coarser at 30 meters, but it has more bands. Spectral comparison here, over on the left, looking at a true color composite. So this is natural color, what you'd see if you were looking out of the window of a plane. Over on the right we have a color infrared composite. So although a true color composite is more familiar to us, if you look at the color infrared composite, it's much easier to pick out that red wetland feature just north of the Winooski River. Another spectral comparison here of Washington, D.C. The true color composite on the left, the color infrared composite on the right. I'd like to draw your attention to the artificial turf field in the center there. You can notice on the true color composite image it's hard to tell it apart from vegetation. However, in the color infrared composite, artificial turf has very, very different spectral reflectance properties compared to vegetation, so it easily stands out. Here's a radiometric comparison. Same image displayed side by side. Over on the left, we're adjusting our digital values. And zooming in here, we can see the effect of adjusting those digital values from having an 11-bit sensor is that we can clearly see that a roof that looks like very similar to all other roofs in the right image, when we stretch that out, appears quite different in the left image. Don't always assume that a higher spatial resolution is better. Over on the left here, we're looking at a QuickBird satellite image, and over on the right, a digital aerial image. The QuickBird imagery on the left has a spatial resolution of 2.6 meters. The digital orthophotograph, the aerial image on the right, has a spatial resolution of 1 meter. However, the QuickBird imagery has a radiometric resolution of 11 bits compared to the digital orthophotograph at 8 bits. What this means is that we can apply stretch procedures to the QuickBird imagery to help us see more information within those pixels. Up until now we've been talking about passive sensors. However, there are active sensors, and these active sensors are increasingly becoming more prevalent in the GIS community. Two examples I'll touch on briefly here. So IfSAR, Interferometric Synthetic Aperture Radar, and LIDAR, Light Detection and Ranging. Both of these are active sensors in that they emit their own electromagnetic radiation through a transmitted signal, and then they also receive that same signal. In the case of IfSAR, the most well-known project involving IfSAR is the SRTM, or Shuttle Radar Topography Mission. In the course of a few days, the shuttle, using radar, mapped elevation at approximately 80% of the Earth's surface at a resolution of 30 meters. Up until that point in time, the best available data for the vast majority of the Earth's surface had been 1 kilometer. LIDAR is an active sensor that's really gaining popularity these days. LIDAR is fascinating in that it generates multiple returns. So that is, a laser pulse is emitted by an aircraft, it can strike the top of a tree, and that signal is returned, but you can also see that you get second, third, and fourth, and fifth returns. The power of LIDAR is that it actually allows you to measure the height of features. Example of some LIDAR products. What you see on the left there is what's returned by the LIDAR sensor. It's known as a point cloud. Each one of those points is a reflected signal from a feature. Over on the right here is an end product resulting from LIDAR, in this case a very, very detailed digital elevation model. In some cases, LIDAR data allows us to make digital elevation models with centimeter resolution.